All right, now we're on segment number 4. I'm hoping this is going to work out for everyone. If it doesn't, then I'll try to re-record it or something. You'll need your books at this point for version 8, page 202 and 203, table 7.1. The same for version 9, page 204, table 7.1. And if you follow the outline here, I want you to consider the following population. The following population, pretend that you have 4 scores in a population. And no, this won't be an Abraham Lincoln speech. 4 scores in a population. Pretend those 4 scores are 2, 4, 6, and 8. 2, 4, 6, and 8. Do you ever get a population of just 4 scores, though? No. We almost never get a population of 4 scores. But pretend you have these 4 scores in a population, and pretend that I ask you to get a mean for that population. Could you actually compute and get a mean for that? So if it is a population, the mean would be represented by the symbol what? Mu. And mu here, if it's 2, 4, 6, and 8, would be a value of 5, right? So that's step 1. Now that seems pretty easy and straightforward. The rest of this may or may not. We have to play a little game now, if you will. And the game that we're going to play is whenever you do statistics, do we ever really have the whole population when we do an experiment? The answer is no. We never have the whole population. So let's just play a little game here and pretend that for this population of only 4 scores, that for this particular study, we have a sample size of just 2. So we're going to actually get all the random samples of n equals 2. So we're going to get all the samples of when n equals 2. So we got 4 scores in the population, and we're going to actually look at all the possible samples when you sample with what we call replacement when you grab 2 scores. So this is actually shown in your book on table 7.1. Let's look at the first sample here. So the first sample, if you were going into a grab bag, if you will, with these 4 numbers, you could first grab the number 2, and then put it back and get a 2 again. So sample number 1, you could grab 2 number 2s. And what would be the sample mean there? If you look across that first row, you get a sample mean of 2. The second sample that you could get, you could draw the number 2 first, and then put the number back, and then draw the sample 4. What would be the mean of that? The mean would be a 3. The third sample would be a 2. And then you get a 6. What would be the sample mean of that? A 2 and a 6 would be a mean of 4. Then you could get a 2 and an 8. And the sample mean there would be 5. And then you could start the whole thing over again. Pull out a 4 first. 4, 2, 4, 4, 4, 6, 4, 8. Can you kind of see the trend there on the table? And then after sample number 8, then you could start drawing another number. The number 6, you could get a 6, 2, 6, 4, 6, 6, and 6, 8. And finally, you might draw the number 8 out first, and you could get an 8, 2, 8, 4, 8, 6, 8, 8. So you could get, and let's just write words down that make sense here. What we just did is we had a population of 4 scores, and what we've just done is we've gotten all the samples when n equals 2. So from that population of 4, we selected all the samples of n equals 2. And so what we see in the final column here in table 7.1, they actually have all the sample means. Can you see all those sample means there, all 16 of them? What I would actually ask you to do there is figure out how many different sample means we have where the sample mean is 2. Look at that chart. How many sample means are 2? There's only 1, right? Only when you get a 2, 2 there. How many occurrences, how many in terms of frequency, are there when we have a sample mean of 3? Well, there are 2 occurrences there, right? 2, 4, and 4, 2. If you look down at figure 7.2, can you see them drawing this distribution? Can you see that they only have 1 mean of 2? Can you see that there are 2 means of 3? How many means of 4 are there on table 7.1 that are drawn in figure 7.2? There are 3 means of 4. Notice for the mean of 5, for the sample mean of 5. There are actually 4 sample means of 5 there. How about the sample mean of 6? There are only 3 sample means of 6. There are 2 sample means of 7 and 1 sample mean of 8. Are you kind of following what I'm doing here? Now, if you were to draw a little curve over that, how would that curve actually look? Do you notice anything about that little frequency distribution? Do you notice that that distribution looks normal? Do you think that's a good or a bad thing? This is a very good thing. If you were to actually draw out a little normal curve over that, you would actually give figure 7.2 a specific name, and it's an important name. You would actually, if you drew figure 7.2, you would be drawing out a distribution of sample means. Figure 7.2 is the distribution of sample means for when n equals 2. It's not just a distribution of scores, but a distribution of sample means. So this is all about lingo here. So we've got a distribution of sample means. What we know is that if we just have a population of 4 scores, and we sample 2 at a time, how does that distribution look? Normal. That's a very good thing because we know a lot of good stuff that we've learned previously about normal distribution. So we know that if we just take even a small population of 4 scores, 2, 4, 6, and 8, and sample n equals 2 for that, that the distribution of sample means has a normal distribution. Now let me ask you this. When you look at figure 7.2, what is the mean of the distribution of sample means? What is the mean? And you may want to write this down. What is the mean? And I don't mean to be mean, but what is the mean of the distribution of sample means? What's the top score there? It's a 5. So the mean of the distribution of sample means is 5. Should that be a surprise to us, or should that make sense? Hopefully you answered that that should make sense. The question is why? Hopefully the reason you said yes, that makes sense, is remember the first task I asked you to do when you got those 4 scores in the population? Remember what I asked you to do? I said take those 4 scores and get what? Get the population mean. What was the population mean? Mu was equal to 5. So we've actually just proven something here. We've actually proven that the mean of the distribution of sample means, that's the mean of figure 7.2, the mean of the distribution of sample means actually always equals the population mean. Whew, I know this is mean stuff. Sorry about that. I'm doing the best that I can here. We've actually learned that the mean of the distribution of sample means is actually the population mean. So this is considered very, very useful. It kind of gets into a theorem your book calls the central limit theorem. We're not going to go into detail with that, but we've actually just proven this. There's one other really essential take-home point here. The essential take-home point of all this, if you're wondering why the heck am I doing this with you? Well, the take-home point is this. The mean of the distribution of sample means is always mu, but the problem we have is when we do a study, how many samples do we get? Do we get to have 16 different samples? The answer is no. We don't get to have 16 different samples. We only get to have 1 sample. And the question that we usually ask is if we get to have 1 sample, there's going to be some error. We'd like to get a mu of 5 for that, or an x bar of 5, but there's going to be some error. And the error, when we get the sample mean, is given a specific name. It is called the standard error of the mean. It is called the standard error of the mean. And actually, going back to that part we just covered a few minutes ago with that new z-score formula, the standard error of the mean is the denominator of the z-score. It's the denominator of the z-score. It's sigma divided by the square root of n. And the basic idea, and I don't know if you're still keeping up with me, I hope you are, but you may need to listen to this and ask a few questions. The basic upshot of this is we want a large sample. The larger our sample is, the better chance we actually have of getting our correct mean. The larger the sample size, the smaller the standard error of the mean. The standard error of the mean measures the distance between your sample mean and the true population mean. The standard error of the mean measures the distance between your sample mean and the population mean. We would like that error number to be as small as possible. The way we make that number as small as possible is we have a large sample size. If you can understand those words, that would be quite useful. So the standard error of the mean is measuring how close your sample mean is to the true population mean. We want that number to be close. So the higher your sample size is, the lower the standard error of the mean will be. So whenever we get a sample, we like to have a large sample size, because then the standard error, anything with error, is good, we want to be small. That denominator of the z-formula will be small, and that denominator of the z-score formula, the standard error of the mean, is measuring the distance between your sample mean, the one that you have, and the true population mean. If we just have a sample size of 1, there's going to be a large discrepancy there, and that's not good. If the standard error of the mean is small, that means that our sample mean is pretty close to the true population mean. So going back to our old formula here with the z-score, the numerator represents x bar minus mu. That is called the treatment effect. We want that to be large. The denominator is called the standard error of the mean. It's sigma divided by the square root of n. We want that number to be as small as possible. The way we get that number to be small is we have a large sample size, and then the SEM will be small. I hope that makes some sense. We tried to cover the standard error of the mean. We went through the outline here. We made a little chart. You don't have to make a chart for your notes. You can have some sort of distribution. Don't go nuts about it. We said the shape of the distribution of sample means is normal. The mean of the distribution is the population mean. It tells us that we can use samples to figure out things about the population. How many samples do we get to have? Well, when we do a research study, only one. What do we want that sample to be? We want the n to be large, because this will make sure that the standard error of the mean is low. And if that is low, that's going to work out well for us. I'll stop the tape there.